Can you hear me? Yeah?
Yeah.
Okay. All right, so I am gonna talk also on behalf of Viviana because she's on vacation this week. We are gonna present the module that we put together again on remote sensing application of hydrology. One challenge on teaching remote sensing for hydrology or remote sensing in general is that it is a rapidly growing field, and that's mostly driven by the new technology of new satellites that every year gets launched. So it's an evolving science. So that makes a little bit challenging. And also it's challenging because it involves it's challenging to teach, especially I think in the undergrad level, because it involves some basics of physics, hydrology, geography, programming, and so on. So the module that I'm going to be presenting is meant to be given an undergrad and graduate level to students that have little to no prior experience in remote sensing. So you will see throughout the modules that we will give basic knowledge related to hydrology, to satellite observations, and to statistics. Before jumping into the module, I would like to just give an overview of the sections that we have in the module. So it is mainly composed upon 4 main sections. The main topics of the sections are, first of all, just to create some fundamental backgrounds related to satellite remote sensing and hydrology. So in this section, we provide some definition, concepts. So we introduce the physics of the electromagnetic spectrums that are the foundation of really remote sensing processes, and all of the various steps that a remote sensor expert will have to go through in order to analyze an image or an ensemble of images. The second, the third, and the fourth section is where we also have created authentic tasks. And so the second section is looking at the temporal dimension of satellite data. The third is looking at the spatial dimension of the satellite data. And then finally, we look at uncertainties and errors associated to the satellite data. So if you see in the main topics, you also see that each of these sections always start with concepts and definitions, exactly for the same reason that I mentioned earlier, because remote sensing involves a lot of different disciplines together. So we have to give some background definitions and understanding to students in order to be able to do the modules and that we provide. So as I mentioned, all of the modules, the sections have check understandings, and I will show you some examples. And then we have 3 main authentic tasks where students playing roles, being managers or science advisor for a government and so on. So then they can use remote sensing images to make their own assessment. So moving on, I would like to show also this other table where for each sections, we identify the learning objectives. And as you can see, we'll start with the fundamentals. We are trying to tackle all levels of the Bloom's taxonomy. So especially the first sections, the first section that is a fundamental will cover really just the lower levels of learning. But then as we move on into section 2, 3, and 4, which are those sections that also have those authentic tasks, we start seeing also higher level of the learning, higher level of learnings, where students will also be asked to say apply those concepts that they that we introduced to formulate or create specific recommendations or formulate hypotheses around, say, causes and effects of hydrology. So this is just really the background of the module. So I think that today what I will do will probably just focus on one of the of this section because the structure of all of these sections are similar in terms of what the context is. So we try to give an ensemble of videos, images, definition, text, and so on. So I'll try again to focus on this, and then if we have any time, I will present you also the spatial dimension and the uncertainty section of the module. And before jumping in, I'd like to thank all of the guides that also provided already comments. They have not been addressed yet, but within the next couple of weeks, we hope to address all of the comments that we have received. So I'm just gonna open all of them to show you kind of like the structure. So you see that all of the sections have introductions and definitions, backgrounds, and then each of these sections, again, I'm gonna try to focus on the temporal dimension, have subsections that go into details of what the students should know in order to ultimately be able to complete the authentic task at the end of each of these sections. So I'll start really with the background of the temporal resolution. Just as an example, if it opens. So it's, as I said, usually our each of our units are an ensemble area, just given by some text definition, and we also try to include videos, typically less than 5 minutes, so short and quick and nice videos, so then the students can look at them and not necessarily get bored by having to look at the longer video or read through a lot of texts. So again, some definitions. When we look at temporal dimension, we have to specify what essentially temporal resolution is, data latencies is. So these are still definitions to define those. And as an example of this specific task, the check understanding questions that we created, they also try to be authentic in a way. So for example, when we talk about latent temporal resolution and temporal latency, we ask the question, for example, to the students, like imagine that you are a scientist that work for the health department, say of the city of Tunis, and you know that Mountain Etna had erupted the morning. What kind of remote sensing observations do you use? What kind of characteristics, temporal resolution and latency would you think that is more appropriate for you to make your assessment whether that plume is going to reach the city of Tunis or not? So these type of, I think, authentic questions, they are quick, but they also help the students to imagine themselves as scientists and start thinking about temporal resolution and why is that important in a real world scenario. So this was it for the background unit. So I'm going to go back now onto the time series part of the temporal dimension. And again, as we mentioned, it's an ensemble of basics and background information. And in this specific time series analysis unit, we are trying to introduce concepts that then the students will have to use for the authentic task. And these concepts are mainly temporal characteristics of a time series and statistical tools that they can use to analyze their data. So we'll start with, for example, some time series basics where we define, in a typical time series like this image, you can have cyclic variations, you can have trends, you can have noise. So part of what a time series analysis means, identify all of those type of variations. And these variations, again, can be diurnal, seasonal, climatological. So again, another video that tends to explain that. And then I think at the end of this specific unit, we also added some link to an existing Hydrology course that I think Hamad built and they're related to climate teleconnections. So as another background, trends, what are trends and why are those important? How do we identify trends? Using linear regression, how do we test for trends using significant testing? And so that's exactly what we have in the next unit, where we give some background and basics of how to perform a linear regression in a time series analysis, how to check for the significant test. And all of this really is just needed because I'm gonna just, go back. All of this really is needed because at this point then the students will be jump into the learning activity. So I'm just gonna go over this. I know that I have 10 minutes past. So we'll look at the introduction. And again, as I said, this is meant to be a very authentic task. So in this specific task, we ask the student to play a role as a science advisor, say of the local government. They want to understand how the local water resources is used and how to use that in a more sustainable and efficient manner. One way that we have to, from satellite to observe how much water has been used and how that is changing from satellite is using gravimetry observation. So that essentially observe what we call in this task terrestrial water storage, which is essentially a summation of all water over land. So soil moisture, loose and soil moisture, groundwater, snow, ice, and so on. So you can imagine that if you are, for example, in Greenland, you might have a lot of ice that is melting. So you might look at this terrestrial water storage, you might see a trend because of the ice is melting. Or for example, if you are in Central Valley, California, or in India, where a lot of groundwater is used, you might see this time series having these groundwater depletion signals into their time series. So what we are asking the students to do in this specific task is to look at a couple of time series around the globe. And I think we actually give them the actual coordinates to look at the time series, and we pick one point in the Central Valley, so they are able to identify, say, a drought, the mega drought that we had. One in Greenland, where you see that ice melting on the time series, and one in India, where you actually see the groundwater depletion signal on the observation. So before going into actually the instruction of the task, we also guide the students on what they have to provide and how they will be evaluated through a rubric, which I don't like the formatting of, but that's what we have. So again, before jumping into the instruction, we also provide some resources. As I said earlier, the field of remote sensing is very broad because it has a lot of different satellite observations and types. So for each of these authentic tasks that we have created, we have to provide some background information so the students know what data they are looking at. So we also try to look for videos that are interesting and funny in a way. So as you can see, there's a video that talks about what is terrestrial water storage and how that can be measured from space, and how these gravimetric observations are actually tracking water from space, and additionally some other resources. To complete this module, I mentioned it here, but this is true for all of these sections. It's important for the students to know some basics knowledge of software such as MATLAB, Python, or Excel, because they have to analyze this data. So as an example for this specific authentic task, as I said, we asked the student to pick a few locations, and I'm just gonna go over one location, for example, here, using this Mascom visualization tool, which is embedded into Hydrology as an iframe. This is a tool that was developed by the Colorado Center for Astrodynamic Research. And it's super nice because you can click on it, and I'm just picking up, for example, a point now in the Greenland, and then for each of the points that you click, it gives you directly that time series, so that the data points that the student can download, so they can get the data directly from here, and they can use to analyze the time series, which means to us finding basic statistics. So what's the mean value, the maximum value, and so on. Identify those cyclic variations, and finally determine the trends, and also checking for the significance of the trends. So finally, one point that's where that high level of learning comes from is that for each of the points that they will have to pick, we ask the students again to imagine to be the science advisor for this specific location for which they have analyzed the time series and recommend to the government how to better manage the water resources. Again, this is just one point in Greenland, but we have a couple of more points that we ask the students to analyze. So I think that's it for the for this specific learning activity. I don't know where to check how much time I have. I probably have 5 more minutes. I will stop here if there are questions, but if there are not, I can also show you guys the other 2 authentic tests. And I'm opening the chat right now, so then I can see if there are questions. Okay, so we have 5 minutes, or 5 minutes have passed? Okay, I think I'll stop here then.
Thanks so much, Manuela. Any questions for Manuela or comments for her about what she's shown us of her module? While everyone is thinking, I will say that I've gone through the module and I found the videos that you all chose and the way that you embedded them with text and images, that you combined the different media, really helped me to understand the concept. So, and your check your understanding questions were engaging, like you said, because you put them in that authentic context. And I felt very validated when I could get them right based on the learning I had done. So
thank you. Thanks.
Thank you.
I have a question in the chat that says, what class are you planning to use this in? So I am teaching a senior level remote sensing of the environment class this fall. So I'm planning to use this for that class. And Viviana is teaching a class that is not remote sensing, but it's more hydrology focused. So she's planning to use this module in that class as well. So it's remote sensing as a tool to investigate some of the hydrological application that she's going to teach in the class.